Let's get started. Let me just check the mic is working or not. Hello. Okay. So we were talking about Pontryagin maximum or minimum principle. In our case, we were talking about minimum principle because we wanted to minimize the cost function. So the problem setting was as follows. I have xt plus 1 equals to ft xt ut, and I have the j of the performance index ct plus 1 plus summation t ct, and we wanted to minimize this cost by picking an appropriate set of actions. And the maximum principle says, or the Pontryagin minimum principle says, is there exists pt star t equals 1 to capital T plus 1 such that pt equals to gradient xt of ht, p capital T plus 1 equals to gradient xt plus 1 ct plus 1. So I'm not writing the argument, I just want to recall the stuff in one side of the board so that I can use the rest of the board for other things. And what else? Gradient of ut j equals to gradient of ut ht equals to 0. This is all evaluated at the optimal solution. And what was ht? ht is pt plus 1 transpose ft plus ct. This is what we had done in the previous lecture last week. We had derived all these expressions and we have showed that this is indeed the first order necessary condition for optimality. So today what I want to show you is how to apply this particular result to devise an algorithm for training neural networks. So neural network, how many of you are familiar with neural networks? The architecture of the neural network? Do you guys know about neural network? No? There are a few people who don't. So let me just try to explain very briefly what the architecture of the neural network is. So you have a bunch of nodes. You can think of them as functions. These functions are all sigma. You have the input vector. Let me call this x naught. So in this case, you have x naught is a vector in 3 dimensions. So you have x naught 1, x naught 2, x naught 3. And then you have let me see. You have the weights here. And the weight matrix is, let me call this U naught to be the weight matrix. And then you get x1 right here as the output. And then it goes through another round of these functions. Sigma is called a sigmoid function. So same thing, we have u1 as the weight of these edges. And so the state transition function here is ft of xt ut. I'm going to denote it by f of ut xt. So ut is a matrix. Let me say ut is in Rn cross n. So it's a matrix. So I'm going to multiply the matrix by the vector xt, and this is given by sigma ut1 xt sigma ut2 xt sigma utn xt, and ut1 utn. So ut1 is the first row of utn is the nth row of ut. So this is how the ut is defined. So ut is actually a matrix here, not a vector, and this is what the state transition function looks like. So state transition function is basically just a bunch of sigma functions that are applied. So the only constraint on sigma is sigma should be non-polynomial and differentiable, like e raised to x or e raised to x over 1 plus e raised to x and so on and so forth. This is a terminal cost problem, so I want the final solution. This is my xt plus 1. So I want my xt plus 1 to be equal to some given vector d. So my ct plus 1 of xt plus 1 is equal to half norm of xt plus 1 minus d square. So this is a terminal cost problem. There is no running cost here. Ct is all identically 0. We only have ct plus 1. Any questions so far? So I have a dynamic optimization problem here. My actions are matrix valued actions. I have a terminal cost. So I can apply the maximum the Pontryagin minimum principle. That's the cost I want to minimize. I want my xt plus 1 to be as close to d as possible, where d is a given vector. And for simplicity, everything is, each of these x is n dimensions and ut is n cross n dimension, but you can have changing dimensions. The rest of the result will not change much, but it's much easier to explain what's happening with only n dimensions here. So what do I want? I want the gradient of ut of j. So this is my j of u. So if I want to train the neural network, I need to know this. So let's try to find out what the gradient of j with respect to ut is. In order to do that, okay, let's try to figure out. So what is my h of t of xt, ut and pt plus 1? This is pt plus 1 transpose f of ut xt. Where ut and xt is getting multiplied here. It's just a matrix multiplication. So ct is 0, so ht is just this term. If you look at this particular equation here, I need to find out two gradients with respect to xt. One is gradient, two gradients of ht. One is with respect to xt, and the other one is with respect to ut. So these are the two gradients I need. Let me write down some expressions. So I am going to define dt as sigma prime ut1 xt sigma prime utn xt. Sorry. So this is a row vector, this is a column vector. This gives you a scalar. I'm computing sigma prime at a scalar. Sigma prime is the derivative, first derivative of sigma. So I'm computing the first derivative of sigma at a specific point on the real line. So this is my definition for dt, and then I have gradient of z of p transpose f So I've computed these offline. You can also compute it offline if you want to, but this is what the gradients are going to look like. Any questions here? You have computed gradient that looks something like this in your assignment 5.
Is that a lowercase p after the W transpose thing?
Yeah, this is all lowercase p. This is all lowercase p. Okay. So you have computed something similar in your assignment 5, question number 1. If you do it again and again for something like this and something like this, then you will find that these are the expressions that will come out of your calculations. Okay. Okay, so I have figured out what the Hamiltonian is. I have to figure out an update equation for PT, and then I can compute what the gradient of J with respect to ut is. So what is my PT plus 1? What is my PT plus 1? It's gradient of CT plus 1 with respect to XT plus 1. What's that equal to?
XT plus 1 minus D.
Yeah. So this is XT plus 1 minus D. That's the gradient of this expression with respect to XT plus 1. So I've figured out what PT plus 1 is. What is P small t? This is gradient of XT, HT. So I'm taking the gradient with respect to XT of this expression. What is this equal to? Can someone tell me based on these two derivatives?
Transpose D.
It's a pattern recognition problem. What is this equal to? Come on, you can be wrong. This is not midterm. Midterm is scheduled next week.
UT transpose D UT plus 1.
Wonderful. So that gives me the update equation for PT. It's just matrix multiplication. Okay. Now what about gradient of ut of J? This is given by gradient of ut of HT. Who can help me with this? Yes.
Can you write the dimensions of UT? Last time in the lecture you wrote it as m time, like a single.
Yes, yes, yes.
Today it's
Today it's a matrix valued
should that
action.
be matrix as well?
So you can stack all of this n cross n matrix as a big vector.
Yes, you can, but I'm just wondering, yesterday it was supposed to be m cross t as well.
M cross?
Like yesterday when we wrote mt as a single vector, should that have been a matrix as well?
Look, it doesn't matter whether you view it as a matrix or a vector. It's just a bunch of independent variables. And you can stack it as a matrix, you can stack it as a vector. It doesn't matter as long as the computation of the gradients are correct. So here, if you look at this vector u, this is what? R n cross capital T. Right? So each ut is Rn cross n, and I have capital T number of such actions. So this is the dimension. In fact, when you see, like, when they talk about large language models and they say, oh, we have 1 trillion parameters, what they are referring to is this n cross T. So that's 1 trillion. Okay, that's what they are referring to. So what is gradient of ut of ht?
dt plus 1 x transpose.
Yeah. xt transpose, right? Yeah. Okay, wonderful. So now I have this equation for computing the gradient. How do I run the gradient descent now? What would be the approach for running the gradient descent algorithm? Sorry. So the way to, yeah, anybody wants to give it a shot? No?
Negative gradient.
Yeah, but how do I start? Like let's say it's very beginning. So I've computed all these expressions, I've written the MATLAB code for computing, doing all this matrix multiplication and stuff. Now I need to start the iterations, gradient descent iteration. So what should I do? What's the first step? What do we do when we start gradient descent? What is it that we pick at the very beginning? Yeah.
We start with arbitrary action values.
Right.
And then we do a forward pass. We
Right.
take an initial state, move it all the way across.
Right.
And get the value of the cost function.
Awesome. So let me write it down. Where should I am going to erase this side. Okay, so I'm going to pick the first, so k equals to 0. So I'm going to pick the entire set of actions from time t equals to 1 all the way up to t equals to capital T. I'm going to store it in a vector. Let me write it as R n cross capital T, k equals to 0. And then you are saying step 2 is, let me write it as 1a. Should I use k equals to 0? Okay, that's fine. We'll use k equals to 0. So and then b is forward propagation. xt plus 1 equals to ft xt ut. So I applied this forward propagation for all time t, and I get xk k equals to 0. So I get entire x1, x2, x3 all the way up to x capital T plus 1 for the iteration number k. Then what do I do?
Backpropagation.
Sorry?
Backpropagation.
Backpropagation. Okay. What should I do in the backpropagation? Let me write it completely. What should I compute?
Gradient.
Which gradient?
For each updating the weight.
Right. Not weight. This is PT, the co-state vector. So this is a co-state vector. Remember the name. So I'm going to compute PT equals to UT transpose, well, PTK, UTK, DTK, PT1K. Right. So I'll compute my backward. I'll do the backward propagation, and I'm going to get Pk, k equals to 0. Now what do I do?
Compute the cost functions with respect to derivative of ut and xt because we know pt for the k differential.
Okay. So D is compute gradient of UTJ. What is that equal to? DTK PT plus 1K XTK transpose. Now what do I do?
Use steepest descent on the actions.
Sorry?
Use steepest descent to update the actions.
Yeah. So then I'll use UTK plus 1 equals to UTK minus alpha k, and whatever this term turns out to be. And then from here I will go back to the same step 1a with k equals to 1. So this is the back propagation algorithm for training neural network. Yes.
The questions about first let's start defining the Poitras minimum. So we're starting from t is equal to 1 to t plus 1.
Right.
So I was wondering, should we start from 0 or 1?
It doesn't matter.
But because the dimension of u will change, right?
Right. I mean, see, the index, where you start the index from, it doesn't matter. Whether you call it k equals to 1 or you call it k equals to 0, how does it matter? The algorithm still remains the same.
0 to t plus 1 or t is equal to 1 to t plus 1? That was
Whenever you start, like in this case, we are starting from x0. So you start from, we are starting from x0. So you start from t equals to 0 to capital T. So depending on which book you read, some books start with x1, some books start with t equals to 1. So then this is t equals to 1 to capital T. Some book will start from 0 and go all the way up to t minus 1, and then they have ct here. So if we start with x0, then this should be t plus 1, and this should be t plus 1, because there are t plus 1 number of actions that you need to pick at every point of time. Okay? Any questions so far? So this is how you apply this backpropagation algorithm. If you use vehicles, if you use electric vehicles, if you use rockets, if you use satellites, almost all of them are running this algorithm all the time to do optimal, to figure out what the optimal action should be. So you don't go from Earth to Moon just like that. You have to apply this algorithm at every point of time to get to the Moon and land at a specific spot on the Moon or on the Mars or on Jupiter or whatever other planet you want to go What is the problem with this algorithm? Sorry? Time taking, well, if you have only 5 states and 100 time steps, it's not really that time consuming. Yes?
Are we assuming it's noiseless?
Kind of, but what happens with the noise?
It's not going to make our gradients precise.
It will not make our gradients precise. Okay, I want you to build up on it. That's not quite the right answer, but you're getting close.
We are not using,
So I have a rocket, I want to send it to moon.
we are only using the terminal cost and not the running cost.
No, we can use the running cost. I mean, this is just a illustration of maximum principle. So we talked about necessary condition. This is a necessary condition for optimality. What's the problem with necessary condition for optimality?
It needs to zero out.
Sorry?
It needs to zero out. The gradient has to equal to 0.
Yeah, remember in minimizing x cube, the gradient was equal to 0.
So the point is, since it is only the necessary condition, the solution may not be minimum. It can just be in stationary point.
Right, so it's just a stationary point. So whatever you converse to is going to be a stationary point of the overall optimization problem. So all the problems of necessary conditions for optimality is here. So first is converges to stationary point. Any other problem that you see? I want you to build up on this noise story. What's the story there? So I have a rocket,
Yeah.
I shot it up, and then what happens?
There's going to be noise in the measurements, and that's going to lead to.
Let's assume that measurement noise is not something we care about. We care more about the fact that there is wind blowing here and there, and the rocket is no longer on the trajectory we thought it would be.
I'm not following you now.
No? Okay. So I started shooting the rocket up, and then the wind started blowing here and there, and now the rocket was supposed to go. Let me draw. Where should I draw? I'll keep it here. So here is Earth, here is Moon, and I shot the rocket up, and this was the trajectory. That was supposed to be optimal trajectory. That's what this particular algorithm told us, is that this satisfies the necessary condition for optimality. Hopefully it is the optimal trajectory to go from Earth to Moon. And I sent the rocket up, and guess what? Because of the wind, the rocket is now here.
It does not go to the global optimum.
Let's assume that the global optimal is also supposed to satisfy the necessary condition for optimality, right? So let's assume that for some reason, through some stroke of luck, we know that this is exactly the optimal trajectory that the rocket is supposed to be on. And because of all kinds of wind, and the bird came and struck the rocket, and I don't know, like a lot of crap happened, and the rocket actually moved here. Now what do I do? Yes?
You have to recompute the whole optimization problem from start.
Right. So now when you stood here, when you're standing here, you now have to recompute. So remember, this one was supposed to be x1. This is my x0, but now this is my x1 prime. This is where I'm standing right now. So now I have to recompute what the optimal trajectory from x1 prime is going to be like. Okay? So you recompute, you redo this entire computation again to get back onto the optimal trajectory, and then you move a little bit more, and now you are here, which is your x2 prime, and then you recompute the optimal trajectory all the way to the moon. Okay? So at every point of time, you have to recompute the entire optimal trajectory, starting from there all the way until the end of the horizon. Okay? So this is exactly how things work in vehicles. This is exactly how things work in all kinds of air conditioning systems and so on and so forth. Wherever they are applying, this minimum principle for optimizing certain things. So in the case of vehicles, they want to optimize fuel consumption. They might want, in the case of wind farms, they want to track a certain production profile. In the case of electric battery, they may want to improve the lifetime of the battery. So all of those requires them to compute the optimal trajectory for the action, and the state changes because of a lot of unmodeled dynamics. There could be unmodeled dynamics because you simplified the model so much that now you don't have the true dynamics of the system. So the things can drift because of unmodeled dynamics. It can drift because of the external noise. It can drift because of some failure within the system. So in the battery packs, it's quite often like the sum of the cells could fail, right? So that could create a problem. So in all these cases, things drift, and so then you need to recompute the optimal trajectory all the way until the end of the horizon. Okay, so you have to recompute at every time need to recompute optimal solution, optimal action. Anything else that you see problematic with this algorithm? So the first problem we found out was it converges to a stationary point. The second problem we found out was, given that there are a lot of issues with our model, dynamics, environmental conditions and so on, at every point of time t, I know that I will not be exactly at the trajectory I had imagined. Now of course things change when you go to the outer space, because in outer space there aren't as many noise variables, but there are still some noise variables. So what are the noise variables in outer space? So radiation, sun's radiation, it tends to exert certain force, okay, on satellite. It's not a very huge force, it's a small amount of force, somewhat negligible, but still when you are in the outer space, you don't really have too many noises to take care of. But as long as you are within these 50 kilometers of the Earth surface, there are a lot of wind and a lot of other things that are going on in the environment, and that can change the trajectory of the rocket. So you need to be aware of it, and you need to take corrective actions at every point of time. So you need to recompute at every point of time. Okay. This particular part is so important that this has a specific name. It's called time consistency. And basically this particular set of solution coming from the Pontryagin minimum principle is actually weakly, it's a weak time consistency, which means that at every point of time t, if you were at the optimal trajectory, you didn't have to recompute the optimal action, but if you are away from the optimal trajectory, then you have to recompute the action. So that's weak time consistency. We'll shortly study about dynamic programming algorithm in this class or maybe the next class, which gives us a strong time consistent solution, which means that once you compute the optimal solution, you don't have to recompute it at all, because that's the globally optimal solution. It's a sufficient condition for optimality. It gives you globally optimal solution, and it gives you a strong time consistent optimal solution, okay, because you don't have to replan. Once you have planned it, you're done with planning. You can just execute it and you can go to sleep without any problem. So that's dynamic programming. What is a non-time consistent solution? So this is the cool thing. So why do we talk about time consistency? Because economists worry about time consistency, because people are non-time consistent. People's plan of actions are always non-time consistent. Now here is a thought experiment. Let's say I bring a cake to the classroom, okay, and all of you are hungry students. You are hungry for knowledge and you are hungry for cake. Okay, so all of you will think about, so your plan of action. So what's going on in your head? Let me write down what's going on in your head. So this is you, this is cake. Okay, and so you are thinking, here is my plan. My U0 star is eat the cake, and my U1 star is go to the gym. Right? All of us think exactly like this whenever we see a cake in front of us. So we'll eat the cake, and then next day, first thing at 6 a.m. in the morning, I'm going to go to the gym and burn this cake out. What happens next day at 6 a.m. in the morning? We don't go to the gym. Okay? So this was my plan on day 0. What's my plan on day 1? U1 star, don't go to the gym. You can of course come up with a lot of different excuses like, oh, my hand is not feeling well, my stomach is not feeling well, I have some homeworks to complete, let's just sleep for another 1 hour, whatever, right? So there are lots of ways to decide not to go to the gym. So what do you see here? It's a time inconsistent. There is time inconsistency. Whatever plan you decided earlier no longer remains optimal at a later point of time. So whenever you are dealing with a situation where there are humans involved in your feedback loop, in your control loop, you have to worry about time consistency. Okay? And it's actually very important. It's very important in a lot of different areas. For instance, in recommendation systems and in other areas. Wherever humans have to make a plan, and that plan needs to be executed. So you don't want to be in a situation where you are trying to execute a time inconsistent plan, because otherwise people will come and say, why did you do that? I didn't want that to happen, right? So it happens quite a lot. So economists, whenever they are doing dynamic optimization problem, economists do worry about time inconsistency, but as engineers we don't, because most of our algorithms go in computing systems, so we don't have to worry about time inconsistency. Anyways, any questions so far? So what is time consistent solution? So time consistent, so weekly time consistent solutions are, if you are at the optimal trajectory, you don't have to recompute. If you are off the optimal trajectory, then you have to recompute. Strongly time consistent plan is, you don't have to recompute again. Okay, it's going to be time consistent throughout the process. So let's talk about, in the next assignment, I will give you one question where this kind of behavior is something that you will see in the solution. So the next assignment will be uploaded, I think, next week, because we have not yet covered dynamic programming. So hopefully today I'll cover it, next Wednesday I'll cover it, and then we'll be ready to do the next assignment, which is the final assignment for this class. Okay. I want to transport you back. So this maximum principle was from 1948, maybe 47, 48, I don't remember exactly, but somewhere around that time, 47, 48, people in Russia, mathematicians in Russia, Pontryagin and many of his students, they came up with this Pontryagin minimum principle. Around the same time, maybe 49, 50, 52, Isaac in Rand Corporation and Bellman, I'm not quite sure where he was situated. I'm blanking on where he was situated. Maybe Florida, maybe not. I don't know. So Richard Bellman. So they came up with necessary condition for optimality. These guys came up with sufficient conditions for optimality. And they came up with what is known as principle of dynamic programming. Maybe this is principle of dynamic programming. So here is the thought experiment. I have to go from A to B. I want to go from A to B and I have multiple paths. I can go like this, covering an intermediate point of C1, C2, C3. I can take this C1 prime, C2 prime, C3 prime, or I can do this C1 double prime, C2 double prime, C3 double prime. So I want to go from x0 to x capital T. I have three different ways to get there. And now the question is, what is the property of the optimal path? So visually, it seems obvious that A, C1, C2, C3, B is the optimal path, right? And the other two are longer paths, so therefore they are non-optimal path. Now what they were thinking about is, what's the property of this optimal solution? What do you think is the property of this optimal solution? By property, what I mean is, what is this AC1 supposed to satisfy, C1, C2 supposed to satisfy, C2, C3, C3B? What are these paths? What are they supposed to satisfy? That's the thought. So the first thing he realized, Bellman realized, is instead of talking about action, let's talk about a plan. So this is known as plan, strategy, law, control law. These are all somewhat interchangeable terminologies. So now the law, control law, is gamma t. Let me use pi. Pi t from xt to ut, from the state space to the action space. Then he said, let me reformulate this performance index not with respect to the action but with respect to this policy. So I'm going to define J of pi as Ct plus 1 xt plus 1 plus summation Ct xt pi t xt. T goes from 0 to capital T, and xt plus 1 equals ft xt pi t xt. I should probably write pi as a vector. So pi phi 0 to pi capital T. Okay. So here was the problem that Isaac was solving. Isaac wanted to come up with very precision missiles. He wanted to kill the enemy through missiles, and it wanted to be on the optimal trajectory at all points of time. Okay, so that the other target is moving, right? So target is probably an aircraft, and he was working at Rand Corporation. It was a top secret research wing of, I think, US Air Force probably. And so he was working there as a researcher. He was also a mathematician, and he was thinking about how to come up with a plan of action for missile so that it can go and kill the enemy, whatever. That was his job. And Richard Bellman, he was in a university, so he was thinking more generally, like what's a sufficient condition for optimality? Like that's the thing that came to his mind. I'm not quite sure what he was looking into at that point of time. I haven't read much about Richard Bellman. So both of them, they were working independently, and they realized that instead of talking about action, what really happens in reality is we move away from the trajectory. A lot of things change while we are executing our action. So we have to be aware of the state, and we need to act according to the state we are in. So if I moved away from the optimal trajectory, I need to be aware of that, and I need to make sure that my actions are actually aware of that particular state. So how do you create that awareness? Well, instead of talking about action, now you talk about plans. What is a plan? A plan takes as input a state and outputs an action. Okay? And then that action is what is applied to the actual system. So instead of talking about the performance index as a function of action, now I'm going to talk about a performance index as a function of plan. And instead of talking about what's the optimal actions to pick, I'm going to talk about what's the optimal plan to pick. Okay? That was their insight. So they wanted to talk about plan, Pontryagin wanted to talk about action. Now the problem is, this is my statement, I want to go from A to B, I want to come up with an optimal plan. Okay? Now what's the property of the optimal plan? So that's the second question. So I have reformulated the problem as a plan. How do I know that my plan is optimal or not optimal? And so the insight that they had was, I want to go from A to B. The plan for the tail subproblem has to be optimal. So I want C3 to be optimal, I want C2 to be optimal, and I want C1 to be optimal. So each of these sub-problems, so you have the original problem, which is a capital T plus 1 time step problem. I am going to divide it into sub-problem that starts at time t, goes all the way until capital T plus 1. And I want to make sure that my plan is optimal all the way until the end of the horizon. And so this is the result that they came up with. Independently they came up with this result, which is called the principle of dynamic programming, which is pi 0 star to pi t star is optimal if and only if pi t star to pi capital T star is optimal for every t (0, 1) all the way up to capital T. This is known as Bellman's principle of optimality or Bellman's principle of dynamic programming or principle of dynamic programming. So pi naught star to pi t star is optimal if and only if pi t star to pi capital T star is optimal for every t. But what is this optimal of? K is already used, tau. Tau equals T to capital T, C tau, X tau, U tau, plus Ct plus 1, Xt plus 1. This is tau. So I'm looking at this subproblem. Okay, this subproblem starts at time small t, goes all the way up to capital T plus 1, but it's only a function of pi t to t because there is no plan at the terminal time step t plus 1. So I'm looking at this cost going all the way from t to capital T plus 1, which comprises of the running cost from time t to capital T and the terminal cost. And I'm looking at this particular sub-problem, sub-optimization problem, and I want for every t, the plan, the rest of the plan has to be optimal for this particular optimization problem. Okay? So this is known as the principle for optimality, is optimal for jt to t plus 1 for every t in 0 to capital T. Okay, so this was found in 1952 by Richard Bellman. He wrote the first paper on it, which went into public domain, but Isaac actually proved it in 1949, but that was a confidential document, so people don't know about it. So now everybody talks about Bellman's principle for optimality or Bellman's principle of dynamic programming, but actually Isaac was the first one to find it out. But anyways, it's called principle of dynamic programming or principle of optimality or Bellman's principle of optimality and so on and so forth. Like there are a bunch of names that people use in the literature. Now what we will do in the next class is based on this particular result, which was proven back in 1949, we'll derive an algorithm. That algorithm is known as a dynamic programming algorithm. So we'll start with this theorem, we'll derive the dynamic programming algorithm, and then we'll try to solve a couple of problems using dynamic programming. Okay. Thank you so much. We'll meet again on Wednesday.